Momentum equals mass times velocity. You learned it in school. You wrote it on a test, you got it right, and you walked away thinking you understood momentum. You don't. And I don't say that to be rude. I say it because for a very long time, some of the best physicists in the world didn't fully understand it either. They had the formula. They used it every day. But they were missing something enormous hiding right behind it. Something so deep that when it was finally uncovered, it changed how we think about the entire universe. So let me take you through this properly, not the textbook way, the real way. All right, let's start where everyone starts. You've got a ball. Let's say it weighs 1 kilogram. You throw it, and it's moving at 10 meters per second. What's the momentum? 10 kilogram meters per second. Mass times velocity. Done. Now I throw a heavier ball, 5 kilograms. Same speed, 10 meters per second. Momentum, 50 kilogram meters per second. More mass, more momentum. Makes sense. Now I throw the light ball faster. 1 kilogram at 50 meters per second. 50 kilogram meters per second. Same momentum as the heavy one going slow. And that feels right, doesn't it? A small thing moving fast can pack the same punch as a big thing moving slow. So far, so good. This is what everybody learns. Mass times velocity. A bigger number means something's harder to stop. A truck at 60 miles per hour has more momentum than a bicycle at 60 miles per hour. A bullet has a lot of momentum for its size because it's going very fast. All perfectly sensible. And here's where people get comfortable. They say, okay, momentum, I got it. It's how much oomph something has. A measure of how much motion something is carrying around. Mass times velocity. Next topic. But hold on, let me push a little harder. Why do we care about this particular combination? Why mass times velocity? Why not mass times velocity squared? Why not mass times the cube root of velocity? Why not mass squared times velocity? You could invent any formula you want. Multiply mass by some function of speed. You'd get a number. But physics doesn't care about random numbers. Physics cares about quantities that mean something. Quantities that nature actually respects. So what is it about this particular combination that's special? Here's the answer most people give, and it's not wrong, but it's shallow. They say momentum is conserved. If two things collide, the total momentum before the collision equals the total momentum after. And that's true. That is a genuine fact about the world. If a big ball hits a small ball on a pool table, you can track the momentum of each ball before and after, add them up, and the totals match, every time, without exception. Let me make that concrete. Take two pool balls. One is sitting still. The other rolls toward it at 6 meters per second. They collide head-on. After the collision, the moving ball almost stops, and the stationary ball shoots forward at nearly 6 meters per second. Momentum before, the mass of one ball times 6 plus the mass of the other ball times 0. Momentum after, the first ball times nearly 0 plus the second ball times nearly 6. Same total. The momentum just passed from one ball to the other, like handing off a package. You can try this with anything. Shopping carts in a parking lot, hockey pucks on ice, toy cars on a track. Set up the collision however you want. Measure the masses, measure the speeds, calculate mass times velocity for each object before and after. The totals always match. It's like a magic trick that never fails. And it works whether the objects bounce off each other or stick together, head-on or glancing, big hitting small or small hitting big. The total momentum before always equals the total momentum after. And that's neat, it's useful. You can solve all kinds of problems with it. Collisions, explosions, rocket propulsion. It's one of the great tools of mechanics. But here's the question that almost nobody asks. Why is momentum conserved? What is it about the universe that makes this particular quantity and not some other quantity stay the same? Most people stop here. They accept conservation of momentum as a given, a rule, a fact about collisions. End of story. That is exactly where the misunderstanding begins. Let me show you the first crack in the simple picture. And it's a big one. Imagine you're standing in a dark room. You've got a flashlight. You turn it on and shine it at the wall. Light comes out, hits the wall. Seems simple enough. But if you had an incredibly sensitive instrument, you would find that when you turned on that flashlight, you got pushed backward. Very slightly. Almost immeasurably, but pushed. The light shoved you. Now think about what that means. Light has no mass. Photons, the particles of light, have zero mass, not tiny mass, not almost zero, exactly zero. So if momentum is mass times velocity, and the mass of a photon is zero, then the momentum of light should be zero times the speed of light, which is zero. No momentum, nothing, and yet the flashlight pushed you. The light carried momentum, real, measurable, honest-to-God momentum. This isn't some abstract theoretical curiosity. There are serious proposals to build solar sails, enormous reflective sheets deployed in space, pushed along by nothing but sunlight. The pressure of light on a surface is extraordinarily faint. On a square meter, the force from sunlight is roughly equivalent to the weight of a grain of salt. You would never feel it. But in the vacuum of space, with no friction, no air resistance, no drag of any kind, that tiny push adds up. Hour after hour, day after day, month after month. You can accelerate a spacecraft to remarkable speeds using nothing but the momentum of photons. Particles with absolutely no mass at all. In 1873, Maxwell predicted from his equations of electromagnetism that light should exert pressure. It took nearly 30 years for experimentalists to measure it. But Maxwell was right. Light pushes, and it pushes because it carries momentum. So either momentum is not really mass times velocity, or something very strange is going on with light. And this is not some exotic edge case. Light is everywhere. It is the most common thing in the universe. If your definition of momentum doesn't work for light, your definition is in trouble. Let me show you another crack. This one's more subtle, but just as important. Go back to our simple collision. Two balls on a table. They slam into each other. Momentum is conserved. Beautiful. But here's what people forget. Energy can be lost in a collision. If two lumps of clay slam together and stick, a tremendous amount of kinetic energy disappears. It turns into heat, into sound, into the deformation of the clay. You can measure the kinetic energy before and after is way less than before. The energy of motion went down. But momentum stays exactly the same. Not approximately, not roughly, exactly. How is that possible? Think about it. If momentum were just another way of measuring how much motion something has, like energy is, then losing energy should lose momentum too. They should be tied together. But they're not. Energy and momentum are independent, conserved quantities. They follow different rules. They're conserved for different reasons. And knowing one doesn't tell you the other. This should bother you. If you think of momentum as the amount of motion, then how can you lose half the motion energy but keep all the momentum? What kind of amount of motion is that? Let me make this sharper with a specific example. Take a 5-kilogram ball moving to the right at 4 meters per second. It slams into a 5-kilogram ball, sitting still. In a perfectly elastic collision, the first ball stops dead, and the second ball takes off at 4 meters per second to the right. Momentum before 20 kilogram meters per second. Momentum after 20 kilogram meters per second. Energy before 40 joules. Energy after 40 joules. Everything is conserved. Clean and tidy. But now change the collision. Make the balls sticky. They collide and stick together. One 10-kilogram lump, moving to the right. By conservation of momentum, the combined lump must have 20 kilogram meters per second of momentum. 10 kilograms times what velocity? 2 meters per second. The lump is going half as fast as the original ball. So what's the kinetic energy after? 1/2 times 10 times 2 squared. That's 20 joules. We started with 40. Half the kinetic energy just vanished. Poof, gone into heat and sound and deformation. But the momentum is exactly the same. 20 before, 20 after. So energy and momentum can behave completely differently in the same event. One gets halved while the other is perfectly preserved. That tells you they're measuring fundamentally different things. Momentum is not energy's cousin. It's not a slightly different flavor of how much motion. It's tracking something else entirely, something independent, something with its own reason for existing. And the reason it's not adding up with the simple picture is that our picture of momentum is too simple. It's too narrow. It's a cartoon version of something much more interesting. So, let me take you somewhere unexpected. I need to take you into empty space, not outer space, not stars and galaxies. I mean the space around you right now, the emptiness between objects, the stage on which everything happens, because the secret of momentum is not about objects at all. It's about space itself. Pick a spot. Any spot, call it here. Now pick another spot 5 meters to the left. Call it there. Now let me ask you a strange question. Is here any different from there? I don't mean is the furniture different. I don't mean is the temperature different. I mean, are the fundamental laws of physics different at here compared to there? If you set up an experiment here, measure everything carefully, record the results, then pick up your entire laboratory, every atom of it, move it 5 meters to the left, set it down and run the exact same experiment, do you get the same result? The answer is yes, you do. Every experiment ever conducted confirms this. The laws of physics don't depend on where you are. They are the same here as there, the same in New York as in Tokyo, the same in this room as on the surface of Mars, the same in this galaxy as in a galaxy 10 billion light years away. Now this sounds obvious, almost too obvious to be interesting. Of course the laws are the same everywhere. Why wouldn't they be? But stop. It is not obvious at all. The universe could have been set up differently. Gravity could have been stronger in one corner of the room. Electricity could have worked by different rules on the north side of the lab compared to the south. The speed of light could have been different in different regions of space. It could have been a patchwork quilt of different physics in every neighborhood. It isn't. Space is uniform, homogeneous, the same everywhere. And we've checked this. Not casually, obsessively. Astronomers look at galaxies billions of light years away, and the light coming from those galaxies is produced by the same atomic processes that happen in labs on Earth. The spectral lines of hydrogen in a galaxy 10 billion light years away match the spectral lines of hydrogen in a tube in a university basement. Same physics, same rules, across unimaginable distances, across billions of years of cosmic time. Physicists call this property translational symmetry. If you translate, meaning shift, your entire experiment from one location to another, nothing changes. The outcome is identical, and this has been verified to extraordinary precision. Nobody has ever found a crack. Nobody has ever discovered a place where the rules are different. This uniformity of space is one of the deepest facts about the universe we live in. It is not a consequence of some other law. It is not derived from anything more basic. It just is, and it has consequences that are staggering. In 1915, a brilliant mathematician named Emmy Noether proved something extraordinary. She proved a theorem. Not a conjecture, not a guess, a mathematical theorem, airtight and irrefutable. Noether was working at the University of Göttingen, and she wasn't even allowed to hold a proper faculty position because she was a woman. She lectured under other people's names, she was paid almost nothing, and yet she produced what many physicists consider the single most important theorem connecting mathematics to physics. It says every continuous symmetry of the laws of physics corresponds to a conserved quantity. For every symmetry there is something that cannot be created or destroyed. Let me be precise. A continuous symmetry means a transformation you can do by any amount. You can shift your lab 1 meter, or 2 meters, or half a meter, or a tenth of a millimeter. Any amount. That's a continuous symmetry, as opposed to a discrete symmetry like flipping left and right. Noether's theorem says find a continuous symmetry, and I will hand you a conservation law. Guaranteed. No exceptions. And it works backward too. Find a conservation law, and I will find you a symmetry. Let me give you an analogy that might help this land. Imagine a perfectly flat, featureless ice rink that extends infinitely in every direction. You're standing on it. No friction. You push a puck. It slides away forever in a straight line at constant speed. Now here's the key. Because the ice is the same everywhere, it doesn't matter where you push the puck. Push it from the center. Push it from the far corner. Push it from any spot at all. Same push, same result. The puck doesn't care where it started. That's spatial symmetry. Now imagine the ice has a hill in the middle. A bump. Suddenly, it matters where you push the puck. Push it on the flat part, and it slides away cleanly. Push it near the bump, and it curves, or slows, or speeds up. The result depends on location. Spatial symmetry is broken. And guess what? On that bumpy rink, momentum is not conserved. The bump can absorb momentum or inject it. The puck can speed up going downhill and slow down going uphill. even with no outside push. The total momentum of the puck changes because space is not uniform. This is not just an analogy. This is exactly what happens with gravity. A ball falling toward the earth is gaining momentum. Where does that momentum come from? From the gravitational field. From the fact that space near the earth is not the same as space far from the earth. The symmetry is broken, and so momentum of the ball alone is not conserved. You have to include the earth and its field in the accounting. When you include everything, the symmetry is restored and the total momentum, ball plus earth, is conserved again. So Noether's theorem doesn't just tell you that momentum is conserved, it tells you precisely when and why it would fail to be conserved when the symmetry is broken. That's an enormously powerful diagnostic tool. And here's the punchline. The translational symmetry of space, the fact that the laws of physics are the same at every location, corresponds to the conservation of momentum. That is why momentum is conserved. Not because of some property of collisions, not because of some accounting trick with mass and velocity. Momentum is conserved because space is uniform. Take a moment with that. The reason a billiard ball transfers momentum to another billiard ball is that the laws of physics don't change as you move from one place to another. The reason a rocket works, the reason an explosion conserves momentum, the reason every collision in the history of the universe has balanced its momentum books, is that space looks the same here as it does 5 meters to the left. That is the deep reason, the real reason. Everything else is a consequence. And Noether didn't stop there. Her theorem gives us more. The fact that the laws of physics are the same today as they were yesterday, that's time symmetry. And time symmetry gives us conservation of energy. The fact that the laws of physics don't change when you rotate your lab, face it east instead of north, that's rotational symmetry. And rotational symmetry gives us conservation of angular momentum. 3 symmetries, 3 conservation laws. Space uniformity gives momentum. Time uniformity gives energy. Rotational uniformity gives angular momentum. The 3 most important conservation laws in all of physics, and they come from the 3 most basic symmetries of the universe. That's not a coincidence, that's the structure of reality. And it keeps going. In particle physics, there are more exotic symmetries, internal symmetries having to do with the way particles transform under the forces of nature. And each of those symmetries gives its own conserved quantity. Conservation of electric charge comes from a symmetry. Conservation of a quantity called baryon number comes from a symmetry. Every conservation law you've ever heard of, and several you haven't, traces back to a symmetry through neither